Today we're going to be looking at the 4.5 material, which is working with the slope-intercept form of a line. We're going to go through a couple different forms of writing out these lines and linear equations, but this is the most common one that we see, and we'll see why we use it most frequently and how it gets its name and applications with that. So our slope-intercept form, general equation for this thing is y equals mx plus b. As we went through with the 4.4 material, m is going to represent the slope. And again, this could be a positive number, negative number, fraction, decimal, zero, anything like that. So m is going to be our slope. B is the y value of the y-intercept. Essentially, remember our y-intercept is 0 and then some number. So in this case, our b value, again, it's the y value of the y-intercept. So these two things are interchangeable. They're going to be the exact same value. So we can write and use the slope-intercept form for all linear equations except for vertical lines. So vertical lines, remember, that's one of those special forms. It's written out as x is equal to a number. And again, the big kicker on that, x is equal to a number, versus this one is y is equal to, and then a bunch of other stuff at the end of it. Okay. So some generalities with this, we need the slope and we need the y-intercept to create a linear equation in this form. Now, need is a particularly strong word to use with the y-intercept. We can technically write out and find an equation of this thing without needing the y-intercept. We could just use a different point, but the y-intercept is by far the easiest point to use to write something into slope-intercept form. Again, primarily due to the fact that we have the slope, and if we have the y-intercept, the y value of that y-intercept can just be plugged in for b from the general equation, and then we're done. We're good to go from there. So this is, again, where it's getting its name. The slope-intercept form, it works with the slope and the y-intercept right after it. So that's the main one of how that came about and the immense amount of creativity, as it were, to give something like this its name like that. So moving on to our next part here where we are graphing using the slope-intercept form. And this is where up till now we've had our methods for graphing, which is, okay, we need to determine at least 2 points, calculate what those points are, and then we plot those points and connect them together. So with this form, with the slope-intercept form, we are essentially doing that same thing, except now we are taking the process of now we don't no longer need to take the process of determine points, calculate them, determine another point, calculate them, and we don't need to go through that entire process if we don't want to. It's still perfectly viable, but now we can use some other parts with this that are going to be really helpful and speed up that graphing process. So the way that we're going to do that, first and foremost, you need to identify the slope and identify the y-intercept. Again, when you are doing this, I think it's extraordinarily helpful to make it abundantly clear to yourself what the slope is and what the y-intercept is. You'd have to be given an equation, which we'll go through some examples of, given an equation, and then write out for yourself, this is my recommendation, write out slope equals or m equals, and then whatever that number is. Write out y-intercept, and then write out what that ordered pair is going to be. Once we've done that, our second step is to plot the y-intercept on a set of axes, which again, we'll need to go through that whole process of setting those things up. So reference back to our 4.1 and 4.2 material if necessary. So we plot that y-intercept, great, and then we use the formula for the slope, rise over run, or the change in y over the change in x, and count vertically, so the rise, and horizontally, the run, to determine the next point. This is where fractions are very, very, very nice when we're working with these. Fractions and whole numbers are fantastic for determining the slope and determining our rise over our run. Make sure that when we are doing this also, we are taking into account if we have a positive or a negative slope, because that will determine if we're moving vertically up or down, or horizontally left or right. And we'll go through a couple, at least an example of showing what that looks like down here. And then once we have our second point calculated using that slope, then we connect the 2 points together and we're good to go from there. And you could use this really to find find 2 points, find 3 points, find 4 points. This will take a lot of the actual algebraic calculations that we were doing previously out of the game and not have it be something that we need to worry about. Now it should be noted in step 3, when we're using the formula for the slope, the rise over run, the change in y over the change in x, some slopes are going to be written as decimals. You are more than welcome, and I highly recommend that you convert those decimals into fractions. It's going to make life a lot easier to do that. And you can do that by plugging that decimal into your graphing calculator and hitting the math frac option. You go into the math option on the left side of your calculator. I think we've gone through one or two of this once or twice. Go into math, the first option, frac, and it will convert that decimal into a fraction right there for you. And bam, now you've got a fraction, and the slope is a lot easier to work with. Okay? So this isn't something that shows up too particularly often, but from time to time we do see it rear its ugly head. But this is, again, all the more reason why we don't like working with decimals and why fractions are nicer. Hopefully my bias isn't entirely showing through, but I think it should become apparent here as we go through some of these problems as to why. So let's graph these two examples that we have using our method that we have right up here. So these are the two examples that we're going to reference as we go over to the whiteboard, or blackboard, I should say. I'm never going to get that right, it seems like. We'll go over to the blackboard and graph these things over there. Okay. So we're graphing these things. Our first one that we were given, we're told y is equal to 3x minus 2. And again, using our new process that we have for this section, identify the slope and the y-intercept. So again, when you're doing this, I would recommend that you write out for yourself something to the effect of slope m equals, and then we're going to reference back to our general form for the slope-intercept form of equations, which is, again, we'll put it up here. Put a little box around this so it stays safe while we're doing and working through these things. So identifying our slope. Okay, so our slope is the value that's directly in front of the variable. It's that m value. So what is directly in front of our variable here? It's going to be 3. So our slope for this problem is 3. Our y-intercept, again, the b value of this equation is the y value of the y-intercept. So it's going to be this guy right out here. It's the value and the sign that is attached to it. So our y-intercept is going to be 0, -2. So from here, we now have our slope, we now have our y-intercept, now we can graph this thing. So we need to set up our set of axes. We have here. So again, all of this, setting this thing up for ourselves, this is something that we have done numerous times now. Nothing is changing in our process. So positive x direction, positive y direction. Got that there. Now, how are we going to scale these things? Well, I'm just going to scale my horizontal and vertical axis by 1s. 5, 5, 3, 4, 5. Something just like that. Okay, now I'm going to graph this thing in red just so it stands out with our points and what we're doing with this. So our second step, to plot the y-intercept on a set of axes. So our y-intercept is at 0, negative 2. It's going to be right down here. Now we're going to use the formula for the slope, the rise over the run, or the change in y over the change in x, either of those, to count horizontally and vertically to the next point on the graph. So looking at our slope, I'm going to rewrite this just off the side here for ourselves, a bit bigger. With the whole number of 3, what is the rise and what is the run? And if it's not directly apparent to you with that number written out in this form, remember that any and all whole numbers are implied to be over 1 as a fraction. So now, referencing our slopes, our two ways of writing the slope, the rise over the run, or the change in y over the change in x, now I'm going to count up, or I'm going to count vertically, and I'm going to count horizontally based on what my slope values are. So what that looks like, do this in blue, our slope is 3, or 3 over 1. What is the sign attached to each of those? Well, for the 3, do yellow here for our change in here. For the 3, that's our rise, or our change in y, and it's a positive number. So it means I'm going to go up by 3. Oops, too much here. It's not showing up very well. Let's try blue, maybe. So going up by 3. Nope, it's not. We'll use the red instead. Stick to that. So there we go. Going up by 3. 1, 2, 3. And then what's my run? What's my change in x? I'm going over by 1. And my new point is going to be right here. I'm going up by 3. 1, 2, 3. And then over by 1 to here. So I'm giving you some extra points that we have, but just showing you the progress of how you would progress from going from one point to the next to the next. Now, that's moving in the positive direction. If we were to do this exact same thing, but go in the negative direction, let's say you wanted to go and plot points to the left of the y-intercept, we'd need to reverse our process. So instead of going positive 3 in the y direction and then positive 1 in the x direction, if we are going to reverse that and go in the opposite direction overall, I would instead need to go down by 3 and then over by 1. Okay? So we can go either way with finding these, finding the next point. We just need to make sure that we are following our directions and our signs accordingly. And again, we only need to find 2 points for this, but I wanted to give you guys some other examples of seeing if we have multiple things written out here for ourselves, multiple points, how can we find those? So we have another point graph, or other points graph for ourselves. We connect these together. And then we have our graph there, and we're good to go. So let's take a look at our second example that we have here. Oops. So we were given y is equal to negative 2/3 x, there x, go, plus 3. So again, identify the slope and identify the y-intercept for yourself. So our slope is negative 2/3. Make sure you are including the sign with that. And then our y-intercept is 0, 3. And again, we need to, let's reference back up to our general form that we have right up here to find our slope, y-intercept. Okay, so we have the slope, we have the y-intercept. We need to make a set of axes for ourselves, and then we can go ahead and graph this. So we have this over here. Okay, so we got positive x, we got positive y. I'm going to count and scale these axes just by ones. So I'm going up by 1, 2, 3, 5. Oh, let's do 9 out here. The opposite direction, then we've had 1, 2, 3, 4, 5, 6, 7. There we go. So again, got things scaled correctly, and we have that there. So for our y-intercept, we're told to plot the y-intercept on a set of axes. So our y-intercept is at 0, 3. So I'm applying that at 0, 3. Now looking at our slope, it is negative 2 over 3. And the question that comes up for a lot of people is, okay, well, does that mean for a rise over a run, am I going 2 in the negative direction for y and then 3 in the negative direction for x? This is where we need to determine, is that negative out front, is that going to apply to our numerator or to our denominator? It can only apply to one of them. It cannot apply to both. So in this instance, if we're working left to right here, I'm going to work with that negative as if it were related to the numerator. So I have a negative 2 over 3. And again, referencing the slope in the top left here. So if my slope is negative 2 over a positive 3, then vertically I'm going to be moving down by 2 places. And then horizontally, that run, I'm moving 3 in the positive direction. So I'm going to go over 1, 2, 3. And my new point is now right here. I could do the same thing again. Let's find another point. So I'm going to be going down by 2 and over another 3. And my next point right there. So again, doing overkill, I'm going by making more points, but I do want to show the possibilities of how we can graph this thing. But it's following that pattern, down 2 over 3, down 2 over 3. Now, let's take the instance where we say, okay, well, instead of having that negative apply to the numerator of the fraction, what if I have it apply to the denominator of the fraction, which would give me a positive 2 divided by negative 3 instead. So if I did that, then I would be increasing, my y values would be going up by 2, and then I'd be going 3 in the negative direction, horizontally, which would put me right here. And I could do the same thing again. I could go up by 2 and over 3. I have that there. So now I've got more points than I really need to have in this problem. I want to show us how we can interpret these slopes and go either way with them, as long as we keep our lines in order for ourselves. So now I have at least 2 points, which is by my bare minimum requirement for graphing these things. I can connect these together, hopefully. There we go. Too bad that time. Connect those things together, and bam, we have our line. So at this point in time now, when we are asked to graph an equation, whether it be on the homework, whether it be on the test, in the Chapter 4 test, we're not going to be, we haven't covered graphing for the Test 1 material, so this would be for Test 2. So when we are asked to graph equations, we do have the option of using our previous methods of determining these points algebraically on a table and then plotting those points like that. Or we can use this method, which is here's a graph, or here's an equation, graph it. And now you have the option of using that table, finding those points, or you can use this method, which would be determining what our slope is, determining our y-intercept, and graph it that way. So both options are now perfectly viable, and you're welcome to use either of them if you would like to. Okay. So I'm going to jump us back to our notes because we're going on to the next part, which is going to relate to some story problems that we're going to have showing up in here. Because story problems aren't going away. Again, spoiler. So this is one that gets a lot of people, because again, this is interpretation. It takes a step back from actual raw numerical calculations and anything like that, and it has us actually assign and put values to these numbers that we're working with in the context of a problem versus just saying, oh, that's just the number 3, that's just -2, or anything like that. So when we are asked to identify or interpret a slope, what a point means, or anything like that, we are not looking at what is the actual direct answer or value. We are looking at what does that number, what does that value, what does that slope represent in the grander scheme of the application or the problem that we are working with. So if I were to give you the number 3, just as a generality, what does this mean in the context of a problem that we're working with? Well, is that number 3, is that a dollar value? Is that how much money I'm making every single week? Is that I don't know how many steaks I'm cooking? We are trying to find out interpret what that number 3 means in the context of the problem we are working with. So interpretations, you're rarely, if ever, going to have a numerical answer to that problem. You're probably going to have a small sentence written out for yourself. And what I find to be really helpful, and a lot of people do not do this, but I think this is very helpful with interpreting the slopes, interpreting points, interpreting anything along those regards, identify what the input and output variables represent, including their units. Now, our input and output variables, primarily, you can think of as what does each variable represent in the problem? Again, there's not going to be any number value necessarily attached to them, but let's say we're working with x and y. What does the variable x represent in this problem? What does the variable y represent in this problem? And be as specific as you possibly can be with this identification process. A lot of people just say, oh, it represents money. Okay, is it dollars? Is it in terms of cents? Is it in terms of euros? Is it pounds? Be very specific when you're identifying that for yourself. And from there, when we know what each of our values or each of our variables represents, then we start looking at points or slopes in terms of that. So if I have the slope, or we relate those units and those identifications to points and the slopes that we have. And this is where the way we write out the slopes of the change in y over the change in x really starts to come in handy, especially with these interpretation problems. Let's say we're making up a problem here, but just making something up. Y represents the money you make per hour you work, and y represents your income, and x represents the number of hours you work. So the change in income based on the change in hours that you work. You might be able to maybe rephrase that could be an hourly rate working somewhere. That could be hourly income, something to that effect. But we identify what variables or what values are attached to which variables, and then start looking at those variables, looking at those points, not in terms of a number or not in terms of a variable, but in terms of the units that are attached to them. This is absolutely crucial to make this possible. So we'll take a look at a quick example that we have here. So we're working with example of Sam drives a delivery van. The equation C is equal to 0.5 m plus 60 models the relation between his weekly cost, C, in dollars, and the number of miles, m, that he drives. So we are told to interpret the slope and the c-intercept of the equation. So the c-intercept is going to be the equivalent of the y-intercept here. Again, if we were to relate this general equation to anything else we've just learned, this is very, very, very similar to our slope-intercept form that we started with. The part that's a little bit tricky about this is we have m representing our slope up here in our general form. And down below here, m represents a variable or an unknown. And again, this is where we need to realize that we can have a single variable. It could represent multiple things. We need to make sure we're identifying what does and doesn't, correspond to a variable and a number. So interpret the slope and the y or the c-intercept of the equation. So the slope of this thing, that is going to be the number value attached to the variable. So the slope is 0.5. So I'll try and see if we can write this thing out here. So I can write it in this. So our slope is equal to the change in y over the change in x. Again, that's our general term with it. So we are assuming, and based on this in this specific instance, it's the same as saying the change in our c values over the change in our, oops, not x, our m values. Okay. So again, interpret the slope and c-intercept in the equation. We are not calculating any values here. We're going to get a small sentence showing up, if nothing else. So I'm interpreting this thing. Well, the change in c over the change in m. Well, what does c represent? The equation c equals 0.5 m plus 60 models the relationship between his weekly cost, c, in dollars, and the number of miles m that he drives. So the change in c over the change in m. So we can think of that as the change in cost for the change in miles driven. Think of it in those regards. And again, a fair amount of these don't need to be perfect 100% accurate, I wouldn't say accurate, but a very specific type of way of phrasing it. There's a few ways that you could phrase that to me, if I'm looking at this on the homework or on the test, as long as it's something in that vein, we're looking pretty good. So the change in cost over the change in miles driven, or something similar to that. And that is how we would interpret the slope. Now looking at the c-intercept. So what is our c-intercept? Well, it's 0, 60. Again, representing or going back from our general form that we have for our slope-intercept form. Oops. Do that. There we go. So again, we're saying, okay, interpret what the c-intercept means. And again, we know what that value is. We know what the ordered pair is. Fantastic. That does not give us the interpretation. We want to interpret what the point 0, 60 means in the context of this problem. Now again, we're going to relate all this back to what does our m variable represent? What does our c variable represent? So if we're looking at this, we have our m value, better m, and we have our c value. So what does m represent? The number of miles driven. So if m is 0, he's driven 0 miles. What does c represent? C represents the weekly cost in dollars. So it means he's going to have a weekly cost of 0, or sorry, a weekly cost of 60. A mistake there. So how could we interpret the y-intercept? We could interpret as at no miles driven, he's going to have the weekly cost is going to be $60. You could also interpret it as at the start of a week, before Sam has driven anywhere, his initial cost is $60. You could also just say his initial cost per week is $60. So 3 ways that you could interpret it. If I was grading this on the test, if I was asking for an interpretation, any of those are completely valid and work no problem for this. So all those would be perfectly acceptable. So then part B is asking for us to find Sam's cost for a week when he drives 0 miles. So for part B, he drives 0 miles. 0 miles, does that correspond to our C or our M value? It corresponds with our M value. So the number of miles that has been driven. So if m is 0, what is our c value going to be? And it turns out that we've already found that. That's our c-intercept. So find Sam's cost for a week when he drives 0 miles. It's going to be $60. So it's our y-intercept that we already have written in the problem, and now we just answer it right there. Part C is asking, find the cost for a week when he drives 250 miles. So we have been given an m value. We've been given that he's driven 250 miles. We want to find the cost. So we would have oh my goodness, come on. There we go. So we would plug 250 in for miles because that's what we've been given. And now we can solve this thing for C, and you can apply your calculator for finding that value. So I'm just plugging that whole thing into my calculator. Oops. 0.5 times 250 plus 60. I'm getting 185. So that's going to be the cost for a week for driving 250 miles. But again, I want to emphasize this, and I cannot emphasize it enough. When we are asked to interpret, so primarily our part A that we had here, look for and go into the problem and find what variables represent, find the units, be as specific as you possibly can be with what m or what the x values represent, what the y values represent, what the c values represent, m values represent, whatever variables we have been given, write that out for yourself or underline it in the problem, something to make, like I did here, something that makes it stand out to you so you know m represents this, c represents this, this variable represents one thing, this variable represents something else. However you can keep that organized for yourself, do it. If that means you have to write something else somewhere else on your paper, go for it. But when we are asked to interpret, you are not finding numerical answers. You're going to have a sentence written out or a short phrase, something like that for your answer. So if you were asked on the test, interpret the slope, and you just give me 0.5, wrong. That is the slope. I want an interpretation of the slope in the context of the problem that you were working with. Okay. So a big difference between calculate the slope, identify the slope, which would be the same thing, or interpret the slope. Okay. So I want to make that distinction as abundantly clear as I possibly can with these. So this is working with interpretations with these overall, which they can and they will be showing up on the homework. They can and they will be showing up on the test, more than likely. Let's move on to our next part that we have here. Okay, so now this brings us to working with parallel and perpendicular lines. So these are ones where we have just some facts that are just stated about the slopes and comparing the slope values and what we can do with them accordingly. So our definitions for having parallel lines to one another is that they have the exact same slope. So the slope of the first line is in every way, shape, and form and value identical to the slope of the other line. So the exact same as one another. Perpendicular lines, their slopes are the negative reciprocal of each other, meaning that if I have the first equation that I have here, the first slope, the negative reciprocal of that is going to be flipping that and making it negative. So we have right here, so a general definition of that. Some numerical examples of the negative reciprocal, because I think it's worth seeing, ones we have down here. So 2 and negative 1/2. So I take the original thing, I flip the fraction, and I change the sign. So 2 is the same as saying 2 over 1. So I flip that fraction, gives me 1/2. And then I change the sign from a positive to a negative. Working with -5 and 1/5, I'm starting with -5. So again, it's implied to be over 1 as a fraction. So I flip the fraction, that gives me a -1/5. And then I change the sign to a positive, that gives me a positive 1/5. So these two are negative reciprocals of one another. And our last one, looking at a fraction, I'm working with the fraction 3/4. So again, I flip that fraction and change the sign. So 3/4 becomes 4/3, positive becomes a negative. And there we have a negative reciprocal of one another. So some other kind of nice, cool, fun facts about perpendicular lines is that perpendicular lines will always form a right angle at the point where they intersect each other. And that's where they cross over on a graph or anything like that. And we actually see this in the original set of axes that we always set up for ourselves, our horizontal and vertical lines that we have here. Okay. So some of the other parts that we have showing up with this, and we'll be asked some questions about it. We'll go through these here in a quick second. But just other questions in general. If we know one of the slopes, we can determine the slope for another if they are either parallel or perpendicular from these properties. So if I were to give you the slope of my first line, let's say the slope is 2. And I want to say, tell me the slope of a line that is parallel to that line, to the slope of the first line. So if the first line has a slope of 2, then the next line that I make, if it's parallel, has to have the exact same slope, which means my new line is also going to have a slope of 2. If my first line has a slope of 2, and I'm asked, what is the slope of a line perpendicular to my first line? Okay, well, if my original slope is 2, then this new line with a perpendicular slope has to have a slope of -1/2. So it's taking what we have been given and relaying it back to our main properties that govern what or define what a parallel and perpendicular line are going to be as necessary. So take what we've been given, determine which of these we are looking for, parallel or perpendicular, and then we calculate what is our new slope, our slope for our new line going to be based on what information we have been given and what we are asked to find for our new slope. So it's slowing down and taking these in parts. Okay. Now we're going to take a look at some of our examples that we have down here, because these are other types of questions that we could be asked. I'm going to go through a couple of these, just go through one or two, just looking at our time, and I do want to give us some time to actually go through some homework questions today. So we're going to take a look at our first two examples on how we could answer these questions over on our Blackboard, and then we'll call things from there. So we're referencing problems 1 and 2, or examples 1 and 2, over on our Blackboard from there. So I'll jump us there now. Oops. There we go. Okay. So our first example was asking us, is the line y equals 2x plus 9 parallel to the line 8x minus 4y equals 24? Okay. So we were given two lines. So I'm going to write those down. So we have those. Y equals 2x plus 9 and 8x minus 4y is equal to 24. We're being asked, are these things parallel to one another? Now again, going back to our definition of parallel lines, if they are parallel, that means does M1, the slope of our first line, is it equal to the slope of our second line? So we need to identify the slope of each of these lines we've been given. Now our first line, the slope is 2. It's been given to us in our slope-intercept form. We know that value right there, done. Our second equation, though, it has not been given to us in our y equals mx plus b, our slope-intercept form. So we need to rewrite it into that form to find out what that's going to be. So I'm going to solve my second equation for y. So I want to get y equals mx plus b, that form for my final answer. So I'm getting rid of that 8x, both sides. So I have that there, dividing both sides by -4. And again, that means every single term is divided by -4. And I'm getting y is equal to 2x minus 6. So now I have my second equation written in slope-intercept form. I need to determine what is the slope. The slope is also 2 right here. Oops. So if the slope of line 1 is 2, and the slope of line 2 is 2, these slopes are equal to one another, which means are these things parallel? Yes. We have our answer. So we need to rewrite our equations, potentially, to determine the slopes of both of them, and then see, do they match the definition of parallel? Do they match the definition of perpendicular? And is that what I'm being asked to solve for? And we can answer yes or no. So looking at number 2, our second example with this, we are told in the problem, is the line 3y plus 2x equals 9 perpendicular to the line 2x minus 3y equals 18? So again, I'm going to write each of those down for myself. So we have our two lines. I'm going to shorthand this, but are they perpendicular to one another? So we need to identify what is the slope of the first line, what is the slope of the second line, which means for this instance, we're going to need to rewrite both of these equations into our slope-intercept form to find the slopes of each of them. So it's going to be some extra work, but we need to do it all the same if we want an answer. So again, trying to find this thing and rewrite our first equation into our slope-intercept form, subtracting 2x from both sides. Being that there. Then I'm dividing both sides by 3 in every single term. So I have that there. So my first equation has been rewritten, and I have a slope of -2/3. Okay, so I now know what I'm looking for my other one in terms of what I can compare it to if I'm trying to find a perpendicular slope. So our other equation, 2x minus 3y equals 18. And again, I'm solving for y here. Let's get into that. And then I'm dividing both sides by -3. Again, that means every single term. So I'm going to get 2/3 x minus, it's going to be 6. Identify the slope. The slope is going to be 2/3. Now, I have the slope of the first line. I have the slope of the second line. Are these things negative reciprocals of one another? Again, so we were looking at this thing, saying, okay, well, one is negative and one is positive, so that's part of the requirement for being negative reciprocals of one another. So that's good. However, the fraction has not been flipped. One is just a positive 2/3, the other is a negative 2/3. To have a negative reciprocal, the signs must be different and the fraction must be flipped. So are these two lines perpendicular to one another? No, they are not. And that's all that we can do. Say these things are not perpendicular, done. Nothing else we can do from there, if that's what we're being asked to do. So again, a lot of these, it's getting everything into that slope-intercept form with parallel and perpendicular at least. And as we're seeing with our first two examples, there are some instances where maybe we don't need to rewrite things into that slope-intercept form. Maybe we will need to write just one of them into that form. Maybe it's going to be both. It's all dependent on what we have been given. So be prepared for the fact that we might need to do that for both of these problems. We might need to do it for one of them. It is not uncommon for that to show up. And it should also be noted, again, it is not uncommon to say, are these things parallel? In this case, we added yes. Not uncommon for it to be, no, these are not parallel. Could be asked, are these two things perpendicular to one another? Well, as we had in our example here, no, they are not. We could have instances where, yes, they are. So it could be either way. We again need to make sure we get into that slope-intercept form and then correctly identify the slopes of each of the equations that we're working with. So this is everything that we have for the 4.5 material, working with the slope-intercept form of these equations. How do we graph these things? Or just a new method to graph these things that might be a bit faster. And how to work with and compare parallel and perpendicular lines, things like that. So this is everything that we have for today. So I will end the recording here.